Could you tell us about Q-deformed string amplitudes?
That's right. Yeah. Thank you so much for inviting me back. It's always a pleasure to visit NYU and its scientists. And now that we're sort of jerking a bit around, perhaps I could also add that the talk that the paper is based, the talk is based on this paper called "Cutting the Kuhn Amplitude." And now I wish I'd stuck with that title, because today is March 15, the Ides of March. So this is the day Caesar was stabbed. We should have stuck with the cutting title. Allow me just to give you like a super brief, like kind of motivational overture before I start getting into details of what exactly these Q-deformed amplitudes and particularly what the Kuhn amplitude is. But to just like super briefly, it was in 1969 that L. D. Kuhn, he wrote down this deformation of the Veneziano amplitude. And then subsequently he wrote like a number of papers about this amplitude with various collaborators, but didn't really manage to attract much attention from the community. But then now in recent years, also with the rise of the S-matrix bootstrap, it's begun to garner a lot more interest amongst our colleagues, especially now that there have been a number of papers these past few years that have presented some evidence that this amplitude might be physical and unitary. So I couldn't resist to include this figure, from Inspire, right? Showing, here you see sort of Kuhn's own papers, and then not so much interest, and then suddenly we have a big spike. So if we were to imitate the Chinese zodiac, right, then perhaps we were designated last year as the year of the Kuhn, the raccoon. So there were a bunch of not just papers that like Inspire is just any citation, right? But these are actual papers that were like directly about the Kuhn amplitude. Now I'll get into more details about what each of these say, right? But a lot of interest from like a lot of institutions. So very briefly, I try to motivate it as to why I think it's an interesting question to try and find out, if this Kuhn amplitude actually represents some unknown physical process. And it's because possibly if it does, it could point to some new physics. We certainly learned a lot from the Veneziano amplitude that we need, that physicists did not first understand. And if it's not physical, it would be nice to know how can we exclude it from exclusion, from these exclusion plots that we get in bootstrap papers. Okay? And then I couldn't resist to just tantalizingly mention that it might have the opportunity, it might provide us with an opportunity to learn some new math. I mean, we know that string amplitudes, they're very closely connected to the special functions that mathematicians study intensely. Okay, so with that, now let's actually start to look more in detail at what precisely this Kuhn amplitude is, right? So here's the form that Kuhn wrote down just 1 year after Veneziano had written down his amplitude. So it's a function of these two variables, sigma and tau, they're typically called. And so they're given specifically by these like linear function of the Mendel-sum invariants, right? And then we have this parameter q, which is a real number between 0 and 1. In principle, you could have q greater than 1, but then you quickly find out that's not a unitary theory. So we'll only be looking at q between 0 and 1. And now this sigma and tau, they're going to be all over the slides. So I hope now you get a good chance to imprint exactly what they are. Well, not necessarily exactly, just sort of roughly you can think of them as the S and T Mendel-sum invariants. So these will appear again and again. So hopefully you can sort of, just roughly remember, right? Like linear functions of S and T, or anti-linear, right? The coefficient is negative. And then additionally, the Kuhn amplitude, right? Besides these two variables, it has sort of 3 parameters. It has q, then the mass, which enters through the definition of sigma and tau, and then sort of indirectly, there's the number of space-time dimensions, which will also play a role. So in principle, it's a function of 2 variables and 3 parameters. So let's start by looking at the poles, right? So just from the denominator, we can read off when we have an S-channel pole. So a simple little exercise you can do, right, is that the poles are at sigma equals to q to the n. So if you just use this definition of sigma, you can solve for s, right? And this is the expression you get, where this little symbol here, these are the q integers, the nth q integer. So it's just a generalization of just adding 1 together a bunch of times as you add powers of q. You can resum it to this expression. Okay. And then what you'll notice is that if we take the limit where n goes to infinity, then these poles converge on an accumulation point at finite s, at this here value.
Sorry, so, the Veneziano, that's at q equal 1, right?
Yeah, that's right. So I'll show you the precise limit. Yes, you're correct. Yeah, that is why I call it a deformation. So yeah, just a few slides. I'll show the exact limit. But then first, an issue to point out is that when Kuhn wrote down in his first paper, he writes down that oh, this could be an amplitude, because it's meromorphic and it has these residues which are polynomial. So by polynomial residue, I mean that if you take a residue in S, right, that's going to be some function of t, and then I mean that that's a finite polynomial in t. Okay, and so Kuhn wrote down these things. So first of all, the amplitude is not strictly speaking meromorphic, but that's more a matter of definition, right? Because usually the mathematical definition of meromorphic is that you have at most isolated poles, right? But the accumulation point is not an isolated pole. Any disk you take is going to have extra poles in it. But I think what really just meant is that there are no branch cuts in the original version of the Kuhn amplitude. Then this issue then of polynomial residues, that's slightly more subtle. I think the issue is that if you just try to evaluate the residues naively, you might do this sort of invalid telescoping of factors, right? But in order to cancel factors between numerator and denominator in an infinite product, you want them to converge separately. So really what you have to do is you have to first divide the numerator and denominator by sigma and tau, right? And then you can perform the telescoping. And so what you find is that the residues are actually, they're polynomial in 1 over tau instead of being polynomial in tau, right? So in general, this is an issue, right? Because
sorry, and is it supposed to be obvious that there are no branch cuts because it's infinite product, so in principle?
Yeah, well, I think it's more. I would say that you can maybe sort of naively imagine that you add like a tiny imaginary part, and then whether you add a tiny negative or a tiny positive imaginary part, and you take the limit where they go to 0. I guess maybe this is not convincing still.
But the way I think of it is maybe it's like inverse of the Jacobi theta function. Like it's crazy on the real axis. Yeah, but it doesn't really have a branch.
But is it obvious from this? Like, is it supposed to be obvious, or it's some trivial change?
Is there a meromorphic change of variables that takes the poles apart? I mean, if you take one over ours.
You're saying so you change, not looking at S, but something else that's different from S, like S and T.
Maybe 1 over S.
Yeah. Well, I guess I'll just be careful about making some non-local transformations in the original S and T.
No, it's not, as long as it's meromorphic, you're
not
changing the meromorphism.
Yes, okay, meromorphism, yes. Okay, I'll just say, like, my pedestrian way of thinking about it is just, if you add a tiny imaginary part, tiny imaginary part, you can add it with either sign, right? And you don't get any like discontinuous changes like you would with if you have a logarithm, right? Where you change the value on it.
That's something which can be just checked.
Yeah, I mean, you could check it numerically for that matter. Yeah. I mean, with all these branch cuts, you really can't check them numerically, right? Like with tiny positive and negative imaginary parts, and see you get the same.
When you place tau to one over tau in your formula, doesn't it residues?
I think it might be related to changing Q to 1 over Q. Like you can play around with it and get polynomial residues in other ways, but but then if you start checking these other conditions, like some of them will eventually fail.
Okay.
Actually, the comment I made about the similarity to the Jacobi theta function is actually not just there's more to that, right? Because I think this equation can be written in terms of ratio of Fock hammers.
Yes, actually.
And I write it in terms of Fock hammers, and I can write in terms of Jacobi theta function.
Okay, well maybe you guys have seen the screen, yeah. Okay, so actually I can show you the. So indeed, I mean the Jacobi theta function, right? It can be recast as like a Weierstrass in terms of like the Weierstrass elliptical functions. So actually, yes, I didn't plan on mentioning in the talk, but actually you can equivalently write the Kuhn amplitude in terms of Weierstrass function, which means also in terms of Jacobi theta.
Okay.
Yes, you can.
And then we know the Jacobi theta function, has these crazy zeros on the real axis.
Right.
All rational numbers. It's a bit different.
Yeah. Yeah. In terms of I'll get to the version in terms of Q gammas, which is the way that it's usually used. Yes. So I'll get to that in a few slides. That too. I guess I'll just first want to fix this issue here, right? And so polynomial residues. I'll get much more into these partial wave decompositions, right? basically having polynomial residues means that the particles you interchange, you know, when you go on shell, right, you'll have some sum over higher and higher spins, so that sum is not going to truncate, right? So that means you have infinitely many particles at every single mass level, right? Which is somewhat undesirable. Yeah, but so you can fix this issue. This was pointed out just a couple of years later, right, by introducing this extra exponential prefactor. So, you know, it's symmetric in S and T, so it doesn't break crossing symmetry. And then, you know, you can write it like this, or equivalently, you could write it as a power of sigma. But then the point is that when we're on a pole, right, so say that sigma is q to some positive integer power L, right, then we have tau to the L, right? So then that means we can multiply each of these factors by tau, and then it becomes polynomial. So this prefactor fixes this issue, but at the cost of now we do have a branch cut. Like now it's clear that there's a branch cut, right? And then yeah, here was the limit you were asking about, right? So now here I chose the specific normalization. You know, I introduced some extra factors of q minus 1, and this factor here as well, right? Which they're just there for normalization to give some nice q going to 1 limit. This particular normalization is the one used by Tolkien and his student Figueroa. I think it's pronounced. Well, I'm not quite sure the pronunciation, but yeah, so q going to 1, you recover Veneziano, q going to 0, you get a scalar field theory amplitude. Okay, and yeah, here then is the alternative formulation I mentioned in terms of q gammas, which I think, at least to my knowledge, this paper is the first one that rewrote in this form. Right, and then yeah, so then this limit becomes transparent, right? Because the q gammas just go to the gamma pole, but you still have this factor in front, right? That factor just simply remains. Right. Yeah, and then.
Sorry. What happens to this factor? Does one recover in some amplitude?
Yes. So this extra prefactor just goes away when q goes to 1, and so basically this, yes. I mean, so for this convention you have a minus sign in front, but you really do just recover the standard Veneziano.
It goes because how does it go away? So there's no q, which just goes to zero there. But
when those depends on q.
No, but there are also the arguments of the gamma function that is 1 over log q, right?
Yes, that's right.
Yeah, in the next slide, right? So you need to.
But it's like this limit is a little non-trivial. Like
so it's not just this factor on its own goes away.
Yeah. So which factor?
Like this exponential factor.
Oh, this factor does just go away. Yes.
But
Can we see it?
No, yeah, it's you have to also let's see. It's the definition. You have to also indeed use the definition here, where then these go to 1.
Ah, so this.
Oh yeah.
Log 1.
Okay, there are log 1, or
Right,
log 1.
0, 0. Yeah.
0.
Log 1.
Okay.
Yeah. So not a score, but.
Okay, thanks.
But yeah, and then of course it's only fair I show you, you know, the Regge trajectories, right? So the usual linear Regge trajectory of the Veneziano amplitude now they get curved, right? And such that they all asymptotes towards, you know, this accumulation level from which the branch cut begins. Right. Yes. And so in a sense we kind of need this have some non-meromorphicity in order to get something that's different from the Veneziano, right? Because there was this paper from 2016 where they showed sort of under some like mild assumptions, right? That essentially if you have a meromorphic amplitude and you have higher spins above 2, then pretty much Veneziano is the only thing you get, or at least in this limit where S and T is large, it will exactly match the Veneziano amplitude. Okay? And so the Kuhn amplitude in a sense is a loophole in the sense that it's non-meromorphic. So that's why in this paper they say, oh, you know, we won't deal with this case. But they do point out that the phrasing they use is they call it formally unitary. And they say by which they just mean that the poles, like the residues of the poles decompose into a positively weighted sum of well, they say Legendre polynomial. So they looked at d equals to 4.
And by non-meromorphic, do you mean here that there is a branch cut, or?
I think I think either of the two, either branch cut or accumulation point. I think. Yeah. I mean, in this case, in the paper, they say the Kuhn amplitude is not meromorphic because of the accumulation point and the branch cut. So
and that paper assumes both, right? That there is no accumulation point. And
that's right. But so since they mentioned this formal unitarity, right, then this paper came out. So this was like January 2022. So there, you know, they refined this partial wave analysis and like carved out specific regions in the space of mass and Q and D where, you know, in some regions they could prove that all the residues were positive. And in some regions they had some numerical evidence that there were critical dimensions. And then there were subsequent papers that looked at these at like leading and sub-leading Regge trajectories and found them to be positive. So this was the mounting evidence I referred to in the very beginning. Then, you know, in addition, of course, to you know, to just these direct unitarity checks, right? Then we also know since this classic paper, like we know that there are additional constraints from causality. There's these like non-trivial constraints on your low energy effective theory. And then in particular, there was Simon Canhuro and Vincent van Duong, you know, computed like specific exclusion regions for these kind of scalar theories. And so Figueroa and Tukin, they explicitly checked. So if you do, when the mass is 0 in the Venetian amplitude, right? Only when the mass is 0, then you can take the limit where ST and U are all small. Right? And so in that case, they did this low energy expansion. And these expansion parameters now, they're going to be functions of Q. Right? So then they plotted them within to see where they lie within these exclusion regions from this paper. Right? And you can see that they lie within, right? That these points represent different values of Q, right? Contrapolating between Q, for Q going between 0 and 1. Yeah. And so, yeah, in a sense, you could say that from like our undergrad quantum mechanics classes, we all know that, okay, accumulation points can be physical in the sense that like the hydrogen atom itself has one, right? Like the energy levels, right, that approach 0 from below. And then additionally, just last year, there was this conjecture by this this like Taiwan group that accumulation point spectra are sort of a generic phenomenon. Although you know, I shouldn't necessarily say that these people think of it as something positive. They even mention, oh, maybe if we could find out how, you know, how to rule them out, you know, our exclusion plots could hone much more in on like the known physical theories. So at least they seem to pop up quite oftenly when you try to do S-matrix bootstrap. But so, you know, if the Kuhn amplitude really is physical and unitary, then we might ask, oh, you know, what other amplitudes might we have missed that one can build from the bottom up? And so there were a couple of papers that performed some systematic searches. And at the end, what they came up with is that if we look at these conditions we've been imposing, and then also including one I didn't mention, right? We do want the amplitude to behave nice at high energy, right? So like specifically, what they assumed in these papers was just polynomial boundedness. So if we assume that, you know, and then additional, you know, polynomial residues and positive partial wave coefficients, then basically the papers they found. One thing they found was this like discrete generalization of the Kuhn amplitude, and then this very recent paper, which came out like I think it was like beginning of March maybe this year. They had this continuous generalization in terms of So here it's written as a sum, but it can also be written in terms of like a hypergeometric function.
Sorry, so was it discrete one? How does it just to Kuhn? Because there is log squared in there.
Oh, but that's just because they use Q instead of an exponent.
Okay.
But so it's these parameters alpha, beta, and gamma.
So I can choose gamma to be equal -1. I completely agree with this.
Oh no, it's in not.
Oh, okay.
Yeah. And so for example, it's like Kuhn has a generalization of there's a Kuhn generalization of the Loveless what's called Loveless Shapiro amplitude, which is then included also as these generalizations. Yeah. And then one observation that these papers shared when they tried to generalize.
So the continuous one also included discrete ones, or
no, I don't think so.
it's a different generalization?
Yeah, I think so. Yeah. Right. Which in principle they point out, like I think the paper wasn't just about accumulation point, right? I think in principle this one also is a continuous generalization of Veneziano directly. Actually, the paper too talks about like generalization of Virasoro-Shapiro, right? Which does not. So the Virasoro-Shapiro are general close-string amplitudes, but those that are no known like accumulation point generalizations. And so this suggested that maybe the endpoints can play some crucial roles, right? Since we can't find the Virasoro-Shapiro versions with accumulation points.
Which of the conditions failed when they tried that?
I'm not sure if it's one specific or it's like the combination of them. But yeah,
what is the problem? Like the structure of Virasoro-Shapiro is very similar to Veneziano.
Yeah.
So it will just do the same steps, like
Yeah, I mean, I guess the simple thing, right, is because the social pure is just gamma functions, right? So you could take Q gamma functions.
Yeah. Same as Veneziano. I'm just saying, like
Yeah. Okay.
Veneziano is just compound.
Okay, I think I played around with this myself, so I can say at least what I too encountered the difficulty is that okay, something similar, right? Is that like I've been showing you a partial amplitude, right? Except when I showed DFT Heathen, right? Mostly I've been showing you a partial amplitude, right? And then you can combine it into a full amplitude, right? And this was also sort of with my number theory preferences, right? Because when you take all three terms in Veneziano, right? You can also just write that as gamma functions, and you could try to Q-deform those, right? You can even write it in terms of the Riemann zeta function once you combine it all, right? But what fails is that you miss the requirement like S plus T plus U equals 4n squared. That plays a crucial role, right? Like that's essentially what allows you to have this cancellation, which I guess what fails are the polynomial residues, because you want things to cancel, like essentially you want this property of the gamma function, right, where it's like you have a gamma function divided by a gamma function shifted by an integer. And so in order for this to work, when you write down the full expression with S, T, and U, you kind of need to use the fact that S plus T plus U gives you a constant.
Not zero.
That doesn't matter too much, but just the fact that S plus T plus U actually doesn't depend on the kinematics. Right? And so that fails because your sigma plus tau plus, I guess I played around with calling it like upsilon, right? So it's S plus T plus U, right? That gives you 4n squared. But if you do sigma plus tau plus and then big upsilon, right? Then that's just going to give you something non-constant. Okay. So then the residues become messy when you try to do something with a full amplitude.
I'm just confused with the difference between Veneziano and Virasio. Like these specs that you said, they don't distinguish between Veneziano.
No, they do because we are social pure, right? There's a full amplitude, so it's a gamma function with ST and U, like it's fully ST and U, U symmetric, not just ST symmetric.
Okay, I see what you're saying.
Right, and so this fact could suggest that maybe the string endpoints are actually crucial. And then there was this observation too that was made. Essentially, Maldassena and Grant Bremen who observed that some of these qualities of the Kuhn amplitude are actually shared if you look at string amplitude where the endpoints sit on D-branes in ADS. Right? So particularly, you can also get an accumulation point spectrum, and you can have this same high energy behavior at large values of S and T. So this behavior you can just read off. It comes directly from the exponential prefactor we wrote down. Right? So you just take the log, right? And then that could get rid of the exponent. Oh, sorry, yeah, there's a typo here. There should be a log. This is log of this equal to this. That's sorry for the typo. Right, but they do also at the same paper they point out that that it's not an exact match. So for example, because if you try to tune the ADS radius such that the accumulation point is at the same value for the Kuhn amplitude and for this amplitude, so you try to match the ADS radius to this Q parameter. If you make them match, then this coefficient will be different for the two theories. So you can match both the high energy behavior and what I guess I call M infinity, right? And actually, there's one more difference. Is that if we look here, right? So for the Kuhn amplitude, this difference between the accumulation point and the regular trajectories, it decreases exponentially. But in this string in ADS setup with D-branes, there it decreases as 1 over J squared. So there are some differences. And so for this reason, there still has not been found a concrete physical theory that can give you the Kuhn amplitude. And then additionally, and this will be really relevant for today's talk, these papers I mentioned look at the poles, right? But the branch cut also needs to satisfy some generalized optical theorem. And so to my knowledge, there was only one paper which appears. This was like coloring large N QCD. This was an S-matrix bootstrap paper. But they mentioned the Kuhn deformation. Actually not Kuhn Veneziano, but Kuhn Loveless Shapiro amplitude. And so there they just mentioned that they did check the positivity of the branch cut, but they actually had, this little proviso inside the scope of our numerical searches, right? So at least it appears that if you just do a quick numerical check, it appears unitary. But so now we're going to try to do, a really thorough systematic check and see if it holds true. And of course, yeah, I guess spoiler alert, it won't, but I think you already knew that So let's just look at these unitarity constraints, right? So I'll quickly review them and the poles, and then we will get to the branch cut. Okay. So this slide, I'm just writing down some equations, which I'm sure are very familiar to the audience, right? That what exactly what unitarity is, and what translates in terms of this T matrix once we subtract out the trivial part. Note in particular, right now I'm assuming we need the incoming particles to match the outgoing ones, for the sake of applying this generalized optical theorem. But we don't need them to be the exact same particles, right? Which is again relevant. We're looking at an amplitude that's only ST symmetric, not SU symmetric. Okay? And then we can diagonalize this by going to this eigenbasis in terms of Gegenbaur polynomials, right? And then the left-hand side is the imaginary part, and the right-hand side is an absolute square. Right? So generally those would be the non-perturbative requirements. But because we're just doing perturbation theory, we're just looking at leading order. That means that we don't we just say this absolute square, that's something positive. So we get some positivity requirement on the imaginary part, or at least even milder, we could just say a non-negativity requirement to be more exact. So oftentimes if I say positive, really you should think of it as non-negative. Like zero is okay. Zero is okay as well, right? So okay, so we want to look at this imaginary part, right? And so for real Mandelstam invariants, we get an imaginary part only on poles or on branch cuts. So here I've written down the Kuhn amplitude again, right? And so the poles, that gives us imaginary pieces, right? Because of, with the I epsilon prescription, there's this distributional identity, right? Where we get the Dirac delta bound. And then the branch cut discontinuity comes from this prefactor we introduce. Right now, owing to you can say owing to the logarithm, or you can just like with the square root. Right? It's like once we have something negative raised to a non-integer power, which generically, for generic values of tau, this will be, we're going to pick up an imaginary piece. Okay, so putting it all together, right? If we so we can write down the imaginary part, right? Where now I'm assuming now that T is not sitting on a branch cut or on a pole, right? So if we're only looking at the imaginary part due to S, right? Then we get the sum over delta functions due to the poles, and then something due to the branch cut discontinuity. Right? And then when we decompose this into Gegenbaur polynomials, so this is like standard physics notation, right, where mathematicians tend to use C for the Gegenbaurs, right, as an argument of cosine theta, where theta is the scattering in the center of mass frame. Then basically all these coefficients have to be positive, or non-negative at least. Okay, and then a brief caveat, right? Is again I'm just checking unitarity now for partial amplitude, right? Even though unitarity really is only demanded for the full amplitude. Right, but that's like for all known open string theory amplitudes, unitarity is present already at the partial amplitude, right? Like that's why we can attach Chan pattern factors, right? We don't need some delicate cancellation between the different terms, right? Like we can sort of adjust them relative to each other because they're separately unitary, right? Even the residues that actually cancel in the full amplitude, the one Feliciano actually wrote down in his paper, the sum of the three terms. Okay, so with that caveat aside. With that done with, now let's look at the poles. Okay, so this is just going to be a quick review now of basically what was already shown in the literature. Right, so it's very simple exercise to find the residues, and then the first residue, just like Veneziano, that's just a constant. It gives us nothing. Well, it's positive, so you could say we pick the overall normalization such that it's positive. Right, and then the first non-trivial residue, we have two Gegenbaurs, and these are the coefficients, right? And so from them we get a lower and an upper bound on m squared, right? And also usually what happens with these string theory amplitudes, right, is that it's like the first non-trivial level is where you read off the critical dimension. Right? Like usually the subsequent levels give you weaker constraints. But these are two rigorous constraints that must apply in any number of dimensions. But then additionally, this specific regime, these two authors prove that all the coefficients will be positive if Q is less than this m-dependent number. Okay, so here's what it looks like if you try to plot it. So basically, this is the red upper bound we just derived, and this is the red lower bound. The two we derived from the first non-trivial residue. Right? And then most papers don't really look at m less than -1. It's also a bit of a weird region. Then you start to, once the mass squared is less than -1, you get multiple tachyons. So a little weird regime. So focusing on the values where the mass squared is between -1 and 1/3, basically there's a regime where you have positivity everywhere, and there's a regime where you have critical dimensions. Or at least numerics suggests that you have critical dimensions below which things are positive. This part is from their paper. where they say, oh, what's the critical dimension as a function of Q for different values of the mass.
So the critical dimension does what?
Well, so basically, for example, if you see this dotted line here, right, that's mass squared equal to -1. So when Q goes to 1, that critical dimension is 26. Then as you lower Q, then the critical dimension drops down, it gets lower and lower, but then eventually goes back up and goes to infinity as you reach, you know, the
So
class Q.
what happens with critical dimension?
Oh, so once you're above, if D is greater than the critical dimension, then there will be at least one of the residues where one of the Gegenbauers will have a negative coefficient. So that was just a super quick view at the constraints we've gotten just from the poles. So now let's look at the cut. Okay, so here again, I'm writing down, reminding us what the Kuhn amplitude looks like. And so this is its branch cuts discontinuity. And then, you know, we want to write this as a positively weighted sum of partial waves. And now we can and will check this just by like numerically computing these coefficients. Okay. The downside there is you just have to, if you do it numerically, you just have to do it case by case for like mass and Q and number of dimensions. Okay. But a different check we can do, which is not complete, but which will allow us to get like some partially analytical handle on these checks, is by looking at the forward limit. Okay. So that'll be the first time we'll look at this forward limit. So the idea now is that these Gegenbauer polynomials, they have this property that when you evaluate them at unit argument, the Gegenbauers and any derivative of them is going to be non-negative. So that means that we have this infinite sum where so if we're assuming all the coefficients are positive, the Gegenbauers and their derivatives are positive, then this left-hand side and its derivatives also have to be positive or non-negative, right? And so here I'm just using the chain rule now, right? To rewrite, like, instead of differentiating with respect to cosine, I'm differentiating with respect to t, right? And then actually this factor we get from the chain rule, we can just get rid of it, because if we're on the branch cut and we're assuming that m squared is less than 1/3, which was one of our constraints from the poles, right? Then this prefactor is positive. So really, this is the condition that we want to check, right? And so we're going to check this for n equals 0 and then 1 and so forth, and check it for the first couple of values of n. But before we do that, just a slight technical aside that I couldn't resist mentioning, because actually, you know, what I just assumed now was that I could take the derivatives and move them through an infinite product. Now, because we've seen before, you know, all these subtleties when you're dealing with infinity, I couldn't resist to actually show you that you can do the check, right? Like this is only valid, this sort of commutation, if the right-hand side converges absolutely. That's to say, if the sum converges once I put absolute values around the sum ends. Okay? And you can check that that's okay to do. Like the Gegenbauers, their maximal value of the derivative with absolute value, it grows polynomially, but the coefficients decrease exponentially. So it's okay. It's okay. And so now we can start looking at the branch cut discontinuity. But actually, even before asking if we have positivity or not positivity, we should ask, are we even dealing with something that's real? So the issue is you can run into trouble if you, in a sense, if you're sort of overlapping between the two branch cuts. So if both sigma and tau are negative, then the branch cut discontinuity actually becomes complex. I think in principle, this is an issue we should think about, even, you know, if everything else came out positive, what it means that we have machines where these branch cuts overlap. But at least, at the very least, we don't want it to happen in the forward limit. Right? And so that gives us a bound on tau. We want tau to be positive in the forward limit. Okay? And so this actually gives us a new constraint on the mass, which, depending on the value of Q, for large values of Q, this is implied by our previous constraints. For small values of Q, it's actually a new constraint. But if we only care about m squared greater than -1, then it doesn't matter. Okay? So, okay, so now let's look. Now we assume now that we are dealing with a branch cut that's an imaginary branch cut that itself is real, or the imaginary 1/i of the discontinuity is real, right? Then you can just simply by inspection here of the equation for the branch cuts. So for the branch cut discontinuity, right? Basically, it turns out that the sign doesn't depend on sigma. So we don't need to worry about the sigma dependency just yet. But basically, this sign function here changes sign, right? As tau goes through integer powers of Q. But then we also have this factor here, which also changes when tau is positive integer powers of Q. So the upshot is that as tau passes through negative integers power of Q, then this whole expression changes sign, right? So this is the kind of behavior that this is the machine where we have positivity. And then using the relationship with, so tau at the forward limit is given by this. So these conditions on tau translate into conditions on the mass. So we can plot them, right? And so in the red regions, I'm showing you, these are the values where positivity are violated. In purple, that's the machine where the branch cuts overlap, and we have, which we don't want, that gave us the complex branch cut discontinuity. Okay? And so if we zoom in on the mass range people typically look at, and then the blue dotted lines, these are the bounds we got from the poles. So basically between -1 and 1/3, everything is positive. So nothing, everything is in agreement with unitarity, we have no trouble. But now we move on to n equal to 1. Okay? So maybe, so this is what you get from differentiating. Let me just quickly show you the original formula. Right? We have an absolute, we have like sigma, norm sigma raised to some power that depends on tau. We have a sine function, and we have an infinite product.
Okay. But remind what capital N was?
It's the number of times I'm differentiating the branch cut discontinuity.
Okay.
Yeah, so I just mean that I'm only differentiating it once. And so, we had a power of sigma raised to something t dependent. So if we differentiate that pulls down a log, right? I've subtracted off I've multiplied by an overall factor of what you had before, right? And then, if we multiply the sine and divide by the sine, we get the cotangent, and from the infinite product, we get infinite sums. Right? So this is just what you get directly from differentiating, right? Simple exercise, we can all differentiate. The problem now is that it's actually kind of hard to read off positivity in this form, because the cotangent has poles, but this sum has poles too, and they actually overlap. And you also want to check positivity for how does it depend on sigma, right? This forward limit check that we're doing has to be satisfied everywhere on the branch cut, right? So we actually have this to be satisfied for every possible value of tau when of sigma, sorry, every value of sigma when tau is at the forward limit value. And so in order to get something that's easier to deal with, we have to massage this expression a bit. So I hope you'll forgive me, but I'm going to give you a few technical details for this check. At least I hope the sort of rough idea will become manifest. But so the first thing to do is I'm introducing new variables. So yeah, my apologies. We started out with lowercase s and lowercase t, the Mandel-Sum invariants. Then I introduced sigma and tau, and now I'm introducing capital S and capital T. Okay? But each of these are just functions only of the original Mandel-Sum invariant, and then the parameters like mass and Q. Okay? And then I'm introducing now a shorthand symbol for these infinite sums that appeared in the derivative. So right now this is just literally just translating what we had on the previous slide. But so now here comes the key identity that'll help us. It's that they're kind of reflection formulas for these infinite sums. And the idea is that like using these kind of reflection formulas, we can rewrite the infinite sums in terms of simpler, like smoothly behaving infinite sums, and we can get rid of these poles that cancel with each other. The price we have to pay in order to use these formulas is that we pick up these extra sort of Fourier series terms with coefficients that are depend only on Q.
Are you implicitly doing some regularization, or all these sums converge?
These all converge. Yeah, you can check this numerically. And then actually these coefficients, right? So it turns out these coefficients, they decrease exponentially. But so if we just look at the leading coefficients, right, the ones that matter the most, right? But these are parameters that depend only on a single number Q. Okay? So even though they depend just on this number Q, they are unnaturally small unless Q itself is very close to 0. So what I mean by, we have some function that depends on a single parameter. We take that parameter to be, say, 1/2, right? And nevertheless, the expressions are like 10 to the minus 12 and 10 to the minus 24. Right? Because we have this exponential suppression 2 pi squared over log Q. Okay?
But you're summing over infinite of.
Yes, that's true, but they decrease exponentially. So like the sum, like it is mostly the leading term that contributes.
Can you show us the formula for alphas again?
Yes. Oh, yeah. Also, these are like the Q-deformed digamma functions, which they're defined just as the usual digamma functions in terms of you differentiate the Q gamma function and divide by, or you differentiate log Q gamma. So in a sense, I mean, this just follows immediately to take the Kuhn amplitude in the Q gamma version, right? These carry over into the branch cut, and then you differentiate them. You pick Q digamma. So nothing surprising there, right? And so, so these are the Q-deforms. And again, I couldn't resist just putting a single sort of mathematical aside, in terms of these tiny coefficients, which actually are going to be the key players in the story, because so it turns out that this pi pi squared over 6, I'm sure you all recognize, right? Like, on a famous solution to the basal problem, right? The problem of determining the sum over the squares of the natural numbers. And so this minuteness we saw in these coefficients, actually that's reflected in a very near miss you get if you try to Q-deform this like basal problem, right? So actually when I first worked on this, I thought, oh, how nice, I found this like nice simple expression for the Q-deformed version, right? You know, because I was like doing Mathematica, checking the first time on 20 digits, but then you go slightly farther and actually there's a discrepancy. And so the reason you get a discrepancy, it turns out that the actual Q deformation of this kind of formula actually doesn't give you the value at a single value of Q. It's a formula that relates two different values, like Q and Q prime, that are related by this formula here. And so this also shows you, you know, at what point the correction starts to become noticeable, right?
That's exactly the S-duality transformation. So think about Q as e to the 2 pi how that's S-duality transformation.
Yeah, I think, I mean,
how to minus 1 over tau.
Yeah, I guess there's a whole story actually, because in a sense, right, you two were talking about these Jacobi functions,
yes.
right? And so basically, right, it's like once you have these elliptic functions, they're defined on a lattice in the complex plane. And so essentially this relation, you know, because so there's a relation between these Q gammas and the elliptic functions. And so this particular relation is like a special case of modular invariance.
Exactly.
Because it corresponds to, so the case when Q is real, is the case corresponds where the lattice is a square lattice. It's like the simplest case. And then this is sort of just a relation, you know, if we swap the two.
That's why
exactly,
it says
exactly, yes. Which is nice. So I wish, you know, if my author story was Kuhn amplitude, it's physical, we found out, right? Then this would be found with other physical implications. But right now, I'm not sure if there's anything beyond, you know, the mathematical facts.
And the B's are non-perturbatively suppressed, right?
Yeah, in Q, yes. Yes, that's right. Yeah, they are non-perturbative for sure. Yeah, I mean exponentials are 1 over log.
Yeah.
Right. So now with these formulas in hand, you know, now having used this sort of kind of reflection formulas for these infinite sums R's, right? Then this is now the expression we get for the derivative of the discontinuity, pulling out these extra factors. And now Q minus 1 is negative. Right? Q is less than 1. So we want the right hand side to be negative. And so this we can try to check. In particular, basically this R plus here, R plus just from its definition is always positive. And what usually happens, which is also what happens if you try to just check this, like naively to check this numerically, and you use, you know, like moderate size, you know, just like some random values for the different parameters, right? Then basically this R plus is totally going to drown out these tiny coefficients we just saw. So really, to get the sharpest limit, what we should do is we should take the limit s goes to infinity. This corresponds to sigma going to 0, right? Like we're on the branch cut, so sigma is negative. So another way of saying it is we're taking the limit now where we are on the s, we're taking s, and then on the branch cut where s then approaches the accumulation point from above. Right? That's the limit we're looking at. So this asymptotic limit, this term drops out. Okay? So just if we take that limit, this term drops out, and essentially our positivity condition translates into this. Right, where basically, let me just go back again. Here, there's also an s dependence in this sum. So we pick s to make this term as small as possible, right, to get the sharpest bound, and you get this inequality, right? And then basically, if you take the limit where this t naught goes to infinity, then this term drops out, and this inequality will clearly be violated, right? But the point is, this limit corresponds to the limit where we go very close to what I before showed you as a purple region, right? So basically, this is like m squared very negative. So you know, this is basically exponentially close to the region we already excluded. But this only applies when Q is, you know, if Q is like order 1. Once Q gets very close to 0, then these coefficients, you know, then they start to become important. So basically, this is the story you get in the exclusion regime, right? Is that you have some excluded regime which is very noticeable when Q is tiny, but then it just asymptotes very quickly towards the purple region we already excluded, right? And this is all, you know, around like, you know, mass is squared less than -1, right? Which is not that interesting anyway. But in principle, already this check at n equal to 1 shows us now that we you know, positivity isn't satisfied between Q0 and Q going to 1, right? So in principle, this already breaks this like nice smooth curve we had of amplitudes. And this was just Q equal to 1. So what if we go higher, right? For higher values of Q. So basically this,
High values of n, right?
n, yes, so n, yes, last values n. Right, so basically what we saw now was taking one derivative, essentially got the discontinuity back and then multiply it by some function, right? And noticeably, this function is periodic in S, right? In this asymptotic limit, right? So in principle, to check for a given value, if a given value of capital T, which corresponds to a given value of like the mass squared, and once we take the forward limit, we really just need to check these G functions in a unit interval, right? And then if we differentiate a second time, you can check that you pull down this other function, which is given by the previous function we had, by performing this operation. And actually, this turns out to be a general recursive fact. Every time you differentiate, you pull down some X overall function, which is given by the previous ones. And you just need to check unitarity in a unit interval for a given value of tau naught, which is a given value of m. Okay? So this is fairly easy to code down. The only thing is it gets numerically become quite cumbersome because once you iterate this procedure, you start to have a very like the function gets longer and longer and more complicated. And so up to about 8 is how long I trusted my numerics for. And you can see, so going up to like 8 derivatives, basically half the values of Q have been completely ruled out at this point. Right? Once we take into account also the bounds we got from the poles. Yeah, but then, okay, so what about this machine? You could, one possibility, right? Like it seems very likely that if you continue going, eventually everything will be ruled out. But what we can do is now we're going to try this other method, right? So that'll be a way for us to look at this region, which so far we haven't touched. Right? So yeah, so now, yes.
So is that when Q goes to 0, you get free scalars?
Yes,
So
yes.
some order of limits?
Yeah, so in principle,
Be careful of that?
yeah, that's right. So right at Q equals to 0, you're fine. But like any arbitrary value above, you run into trouble. Like another way, you could also say, for example, this branch cut, right? Or like
It should go away.
yeah, it goes away also when Q goes to 1, right? And you could say, in fact, when you go to Q going to 0, it's even simpler, right? Because all the higher poles go away. So indeed, so there's a subtlety about the order of limits. That's right, yeah. I agree. Q equal to 0 is fine. Yes.
So but Q equal to 0 is what a scalar with mass m.
Yeah, or maybe the mass has maybe the mass has the wrong sign.
But what are the interactions of the scalar? Because you have a 4-point amplitude.
Well, I think they all go away. Like.
There's 3.
Oh, sorry. The interaction. No, sorry. Yeah, there's a 4-point function. Yes. So, but like the overall normalization, I don't know.
But is it like a normalizable theory, or is it not a normalizable theory of a scalar?
Right. Yeah. I guess I'm also being agnostic about the number of dimensions. So I guess it depends on capital D, because it has the same limit in any D. See, I showed it. Right. Yeah. Right. So, essentially, it's like in principle, right? This is like 5 to the 4th theory with this extra interaction term.
Phi Q.
Yes. Sorry. Phi Q. Yes. Yeah, or Phi Q plus 5 to the 4th with this term. So I guess you have both terms, right?
And the -1 means that the lambda Phi cube is positive or negative? So negative.
Lambda 5 to the 4th.
So yeah, lambda Phi to the 4th is with lambda
Yeah.
negative.
Okay. So actually, truth be told, I think it has the wrong sign. But also, I was a little bit confused by this because the paper where I took my normalization from, they also have this formula, but they have the other sign for the constant term, which I think is a typo. So I think it's the wrong sign. Yeah, I think we would actually want it to have plus. But yeah, it's annoying that they have this typo too, because then that makes me second guess everything.
But that sign is not a big deal.
Yeah, I know, but
Well, I mean, for stability.
Well, but we have tachyons here, right? So it's less bad than tachyon because there is no classical instability.
But I mean, Phi to the 4th is worse than a tachyon, right? Because you had a tachyon, you could just shift it, and Phi to the 4th was positive, then you would sit into some other vacuum. You have a scalar potential with where Phi gets a valve, but
Even if you take literally the zero, but
yeah, if you take literally the terror, it's a scalar, right? I mean, the scalar is a scalar, so you can look at the potential and see if the potential makes sense. Now, if I take your numbers at face value, it seems that your potential is positive. I mean, it's unitary, but it's unstable.
yeah. And then I know you could imagine having higher order terms maybe, but
Supposed to this amplitude should be complete, but there should not be any other corrections to this.
There's a tree.
It's a tree level.
There's a tree level. So you can have 5 to 6 and
Right.
Right, oh yeah, I was at the numerical evaluation. So maybe I won't belabor too much. I guess the point was we saw just from our previous little exercise, right, that we saw the unitarity violations happening in a region that's like exponentially close on a scale set by Q to the accumulation point. So we also know, okay, that's the region we should look at in when we do numerics. We also know you might need to go to like pretty high precision in order to see it, right? That's like a lesson we learned. So we should take that in mind in order to do these numerical checks now. And so one trick to do is that, you know, we derive this kind of asymptotic expression close to the accumulation point for the derivative. So we could just integrate this and get some asymptotic formula for the branch cut discontinuity itself, up to some overall function of s that we don't know, right? Just because we're differentiating the log and just with respect to t, so we could lose some s dependency. Okay, but that's okay. So basically, yeah, and then this factor we get a factor now for the discontinuity, which contains these tiny harmonic coefficients, right? Which we know are going to be what decides if unitarity is violated or not. And then, since we don't determine this function g of s, we can't quite impose positivity directly on these coefficients. Right? Like we can extract these coefficients using the orthogonality relation of the Gegenbauer polynomials, right? The orthogonal polynomials. But we don't know this overall coefficient. So in principle, we don't know if this should be positive or negative. And it could even change depending on s, right? But at the very least, it should have the same sign for all values of j at a given value of s, right? That at least has to be true. And that we can check. So yeah, here I'm using the orthogonality relation. We perform a numerical integration, and that way we can get the coefficients, right? And the only thing is, yeah, this t just gets a little complicated, right? Because t depends on tau, which is a function of t itself, and t itself is a function of the scattering angle, right? But okay, but you know, it's not hard to do on a computer. And so you do this check. So here it's for you know, massless case, 4 dimensions q equals to 1/2. And so you start out with some positive values, some like positive order 1 values, and then they decrease, right, as we go to higher and higher spin. And then eventually, once they're small enough, then we start to see the fluctuations due to these harmonic terms, right? The harmonic terms with the b coefficients, the b plus, the b minus, right? And eventually, the overall coefficient becomes so small that these tiny coefficients actually can induce negative values, right? And that so that positivity is violated.
It seems to be this number's too small to be trusted.
By our numerals good enough to.
Yeah, no, I mean with Mathematica you can do, you know, several hundreds. Like,
I know.
It's also, I mean, you know, sometimes it's like the overall size doesn't matter. Well, I guess in this case it does because it relies on a cancellation and an integral.
Yeah.
But this is definitely within, you know, what you can do.
Did you ask it to give you error estimate?
Yeah, no, for sure, you can.
Is your processor Intel? It's very important.
Yeah.
AMD makes mistakes.
I see. Well, you know, I hope I would avoid these kind of questions by showing the numerics second, you know, in the presentation. But then you're already prepared for the negativity. But yeah, no, I'm fairly confident, yeah, that I'm not worried about numerical issues. And then, you know, you can do this check, you know, just do it across, like the behavior you see here is universal, you know, across different values of j and m squared and d. You start out positive, but eventually, once it becomes small enough, you start to see the wobbling, and then the wobbling causes negative values at large enough values to spin. So just here I'm tabulating it for different values of the mass squared, different values of q, right? And indeed, you know, it's also, you know, in line with our previous analysis, right? When q is quite small, then we see these violations quicker than we would have otherwise. In the sense that, like, we don't need to go to as high spin, right? Because the harmonic, these oscillating coefficients get, you know, start to become large once q is close to 0. Okay? And then yeah, so in principle, the numbers depends on the number of d, right? The number of dimensions, right? Because the partial waves depend on d, right? But it just happens that the first appearance of negativity is the same for the d's, you know, for these values of the parameter, they're the same for d, go between 4 and 26. Okay, so basically we see these positivity violations everywhere. Okay, so to summarize, right? I was first trying to give you an overview of the picture that's sort of been formed, where it's that we have this Kuhn amplitude which looked unitary and interpolated between Veneziano and some possibly quite pathological scalar field theory in these limits. But now we see that like the branch cut analysis, it at least presents an obstacle to this picture, because we're not seeing what we would expect from positivity, namely positively weighted sum of partial weights on the branch cut discontinuity. And so just like some vague possibilities to speculate on. One is that we can fix the Kuhn amplitude. Just like we had this issue of non-polynomial residues, which was fixed by introducing this extra prefactor, maybe one could introduce an additional prefactor to fix the negativity. And it's not entirely far-fetched, actually, because it's just like if you know a function at all the integer values, right? It's a bit analogous. The function was fixed on all the poles, right? But knowing a function on the integer values, you could add any like sinusoidal thing on top, right? Without changing it. So similarly, for this Kuhn, Kuhn amplitude, you could multiply by a function that looks like this, right? And now this has been tuned such, right, that when you're on a pole, then sigma here is equal to the power of q, which means this whole cosine just gets shifted by an integer, which means that this term cancels with this term, right? So like modifications like this are going to leave, are only going to change the residues by a positive constant. So so all these unitarity analysis will carry straight through. In principle, you have infinitely many parameters you could tune here to try and fix these branch cut issues. Moreover, because we saw that these issues specifically came from these kind of sinusoidal terms, you can actually check that if we could just multiply the branch cut discontinuity by this kind of function, right, then we exactly cancel the coefficients, right? And that would actually get rid of all the negativity that we've observed. The downside, though, is that we cannot immediately multiply, this function, the amplitude, by this function. Because once we multiply this exponential factor, it itself has its own branch cut discontinuity, right? Owing to these logarithms, which will propagate through the cosines and give. So basically, for each term in this sum, you get a new branch cut discontinuity. Then you would have to add them all together, and you get cross terms. It becomes a nightmare. But potentially, you might think, what if I were to use elliptical functions, right, which are periodic in the imaginary directions, such that you don't have this extra branch cut discontinuity. The issue there then is that Liouville's theorem tells us that any non-constant elliptic function has a pole, right? Which means we would have a pole and an exponent, but we don't want an essential singularity, right? Then one possibility, which I don't want to be entirely dismissive of, is that since we don't know the physical mechanism, it's hard to rule out that there could be some subtle way that these positivity requirements are subtly a chain somehow for this mechanism, or perhaps some way that you create a full amplitude from the partial amplitudes. And also there were some recent papers which were like a bit more sort of open-minded towards, like, who were less dismissive of this issue of polynomial residues and try to argue why that might be still some relatively acceptable unitary theory. On at least I was a little puzzled by this S-matrix bootstrap paper, which in the exclusion region for Loveless-Shapiro, they showed the Kuhn Loveless-Shapiro inside that plot, but for some reason the one they showed was the one with polynomial residues and no branch cut, instead of the version with a branch cut but no polynomial, but with polynomial residues. Yeah, so for some reason they chose, you could say the original version without the prefactor to show that in the exclusion region.
What do you mean? It's like included or it's excluded?
It's inside. It's inside the allowed region. Yeah, the one without the branch cut. Yeah, and then finally, it's also, I guess we also have to admit the possibility of this sort of the case that the Kuhn amplitude might just be non-unitary, right? At least we know that, like, when you have some theory and you try to generalize it continuously, right? There might be some non-unitarity which is well hidden. Like in the case of continuous dimensions, we have these evanescent operators, right, which you might not notice at first. If you take an ON model, right, then you can get these the spooky operators, as they were labeled in these papers, right? And you could also imagine that it's actually, to get the Kuhn amplitude, you have to Q-deform space-time itself. So there was an amusing footnote in this paper by the Brown group, where they say, oh, maybe one should use the Q-Gegenbauer polynomials. And they said maybe the theory is not unitary, it's Q-nitary, they called it. So I don't know. Yeah, I mean, honestly, if you were to ask me, I would say I would maybe be roughly evenly divided between there being some fix and the amplitude just simply being non-unitary. But maybe I try for a bit to find that fix. So maybe I'm a little less optimistic of that now. But I think basically, right, like over the next few months, people, someone will find the fix, or probably there isn't one, right? So I think maybe over the next couple of months, this question will will automatically provide us with an answer. All right, that's all I have. Yeah, thank you for listening.
So what about these other generalizations which you showed in the beginning?
Yes. So basically, I think for the discrete generalization at least, right, which include also this Lovelock-Shapiro, right? I mean, basically there you're just like shifted the trajectories, you know, like up or down. So I think almost certainly you're going to see exactly the same thing because, you know, like basically in the formulas, right, it's just like an extra leading term that you change. You still have like the reflection formulas, you're still going to have these oscillating terms. So for sure that'll be there. Then there's this continuous generalization, and there I really don't know because it's like, you know, that's a totally different, more complicated function. So yeah, I think that might actually be an interesting project to try and play this game for that amplitude. I think for the others, it's almost going to be a very, very simple follow-up to this.
I have a similar question for the ADS.
Yeah, so I mean, basically my case is that like I would say they pretty much have to be unitary. I mean, these are physical amplitudes.
Oh, right, just to see how that.
Yeah, I guess the issue is just that, like, you know, they're known in certain limits, right? So to perform these kind of subtle checks, then you know, if someone computes, you know, gives a full expression, then yeah, then I think for sure it has to work out and probably interesting mathematically to see, you know, like the properties of the special function such that it all works out.
Okay, but I guess you were checking in the forward limit, so that's not where they have. Where do they have this?
Yeah, the limits. I think one of them it's like large S and large T. You could also say, yeah, we were interested in, yeah, you know, we want to look right at the branch. I guess that's really, really interesting.
But, I mean, in the ancient times, the first sign that there was something wrong with D less than 26 was when trying to glue together three-level amplitudes and compute loops. So, do we know how to do even one loop in this amplitude?
Yeah, I think. Based on my business, I think Kuhn wrote a bunch of papers in the beginning, I think both on higher points and potential loop amplitudes. I think my impression from the modern papers is that basically they don't just distrust any of the early papers and do everything over from scratch.
But you need the internal particles now also on the external legs.
Mm-hmm. So you need to know that the internal particles.
You need to know the amplitudes where some of the internal particles are external.
Also, given that there is branch cut already in the hidden amplitude, so we're supposed to think about that. Yeah. Because there you have three-level amplitude. Here it's.
Are you supposed to glue them together?
Right, but yes.
And by the way, a related thing, do we know the amplitude for more than 4 particles? And
yeah, basically, I know Kuhn himself wrote down expressions like candidate for higher points. Which the only thing I'm trying to remember if that was before or after 1973, and I think they might have been before. So before even that, this, you know, basically versions where they were non-polynomial, and then also the way he wrote them down to were infinite sums. So what I mean to say is that at least there would be another obvious candidate because like if you take the Kober-Nielsen at 5 point, right? Like there you can carry out the integral and you get some sum of hypergeometric, I think it's like 3 F2s, or I'm not sure which ones, right? But these hypergeometric functions do have Q-deformed versions. So there are like some obvious candidates, yes. I guess my own personal view was just, I feel like, you know, if there are issues with a 4 point, right, then I feel like only once those issues are fully fixed, then I think, you know, then I would start, you know, really thinking about the high points. But yeah, I mean, you know, when people really believe this, they also did write down high points.
So those original Kuhn amplitudes which you have done polynomial residues, that's positive, right?
Yeah.
So maybe I should think about those.
Yeah.
Because also they don't have branch cuts.
Yeah.
Yes.
Okay, they have infinite number of particles.
Yes. That's also the same feature, qualitative feature as the amplitude in the ABS, right? You also have accumulation point, no branch cut.
Yeah.
And it's definitely positive.
I guess that's like this.
Does it have polynomial residue?
I guess, yeah, one thing I hear people say, right, is this thing of exchanging infinite many particles. They say that, you know, in a sense, it's like you can have infinite information, like, you know, in a finite region. That would be like in a black hole. Like, basically, I think at least one thing I see in these discussions, I think especially in the Clifford Chung's first paper with Grant Remen, where they say that they think of this as like you're scattering an infinitely extended object. This is the way they phrase it.
But isn't it bad also for thermodynamics? You get infinite entropy factor.
Yeah, I don't know if you can escape it somehow if you smear it out over all of space-time. I'm not sure, yeah. For sure one would have to think about this issue. Yeah, but it's definitely true, you know, like all of the maladies come from this down branch cut that you get as soon as you have this factor. Yeah, and actually I wanted to, you know, this is part of the reason I mentioned this paper, right? I've been tempted to ask them, why did they not include the version, you know, with the prefactor, right? I'm wondering if it actually fell outside the exclusion region. Because if that's the case, right, then that would be a strong argument that one should look at the version without the prefactor.
And if one takes one without prefactor, so in Sana limit, so what happens? So that basically there is like infinite set of particles decouples at each residue.
Yeah,
so
yeah, yeah. That's right.
Yeah, so in that sense, that looks like a better starting point to me, at least.
Yeah.
It looks like some 3-level amplitude without branch. Actually, having branch cuts, I'm not sure then on its own, it's not clear maybe what was the goal, right? Because the goal was construct 3-level amplitude.
Yeah, but I guess then on the flip side though, right, like the fact that they had this extra, the extra prefactor is what gave them the same kind of large energy behavior as these ADS amplitudes. But I guess you could, but then again, I guess you could say, but they didn't match fully anyway, right? So
Yeah.
why should we do this to get a partial match, which doesn't work?
So if I take your exclusions as gospel, what do you think? Are they like slowing down at all? Do you think they'll like stop at some Q, or do you think they'll go all the way to Q1?
I think I think they'll go all the way. I think so. Also, just, you know, because then at least, you know, in the other method, I could do like Q equals 0.9 and I still see it. Like, I guess an idea I toyed with, I was tempted by originally, was that, did you remember there's this Q infinity? Okay, let me just go back. So, here I talked about this Q infinity, that like they had a proof that, you know, you have unitarity in any dimensions if Q is less than this value, right? Q infinity, so it's marked here with a diagonal line. I was tempted to think, oh, maybe it would asymptote towards this Q infinity, because it sounds too good to be true, right? That you have unitarity in any number of dimensions. So maybe this would go away and you would only have a region with critical dimensions. But then, you know, once I went high enough in n, then it starts to intersect to cross this Q infinity region. And then these dot lines numeric checks. So then I started to think, okay, then it's probably the same.
Well, maybe one question actually is before, when you look at, you have theories that are unitary, I mean, 4 dimensions, you can take a Fermi interaction, and then there the problem is like more normalizability on one hand, or 3-level unitarity in this sense that it's not really unitarity, but you look at the scattering amplitude and you see that at a fixed angle it grows too fast with energy. So how do these things grow with energy at fixed angle? What's the behavior of Kuhn?
No, yeah, they are. Well, wait, I get if it's exponential suppression or if it's. I think it depends, right? If you take the fixed angle or regular limit, they're both
fixed angle.
Yeah, fixed angle. I think that might even be. It might even be like exponentially suppressed. Like
even with that prefactor.
Yeah. It's the high energy behavior is definitely smooth. I may be saying not the exact version, but that definitely has been checked and is benign.
Thank you,